Quick test. Can anyone hear what I'm saying? Testing out a new microphone. Let me know in the chat. Sweet. Glad you could hear. I am going to start this today with a bit of an overview about the compiler because I know that's going to work. I know that my streaming setup can handle that easily. And then I'll attempt to do a transition to the kitchen where I show how to mix a dough. That part is going to be a little bit sketchy because the way I've set that up is I have my phone, which is going to be doing WebRTC video to OBS, and then I don't even have a tripod for it. It's going to be hanging from the cupboard with a view of the counter. So we'll see if that works. Otherwise, I will, I don't know, maybe record something on video and post it later. So okay, I'm just going to go ahead. There's only 2 people, but you 2 are lovely, and you want to learn about a compiler. So here, let's take a look at what we've got so far. Little bit of background. I am currently working on a Lisp compiler. It takes in Lisp code and compiles it to x86-64 machine code. It's written in C. It follows this tutorial by this guy Ghuloum, and it sort of loosely follows it. I'm following chapter by chapter. I'm writing installments as well, but you know I can't share any code, and we diverged a bit as far as stack allocating variables in the beginning, but that's fine. Winona, the bread is coming a little bit later. I decided, since that's the sketchy part of the stream, live kitchen shenanigans, I'll be doing the rock solid part, which is screen sharing. That's a little easier first. But why don't we just dive right into the compiler. I have this compiler set up in a couple of layers. First, we've got these sort of object layout definitions, some types, some tags for things. I'll get into the tags later. Some helper functions for poking at pointers and seeing what type they are, because we encode types in pointers. Also for things like pairs, you know, pulling out the car in the cutter. We do treat the tree objects a little bit differently than the Lisp objects. This is because I didn't want to do all this finicky pointer nonsense in the compiler itself, and also it's much easier to do that in assembly than in C, I think, especially with struct padding. Anyway, there's the object helper functions. And we've got this buffer, which is a byte array. It's an expandable array of bytes that holds some more state about if it's currently writable or executable state. It's not going to be both of them at the same time for security reasons. So we'll be able to write code into it, and then we'll switch it to executable, at which point we can no longer write. I think this is fairly safe. And then we've got this sort of x86 layer, which describes the registers, describes some condition codes like overflow, equal, that sort of thing. And then we've got you know, scale, index registers, that sort of thing, and a bunch of functions that are used to encode instructions. So like shift left a register by some 8-bit immediate, blah, 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 blah. bunch of functions like this, a lot of them. And then we've got this tree structure. And this tree structure is when you type in, like let A be 1 in A, that turns into this tree structure containing mostly pairs, because that's what glues it all together. But you've got symbols, you've got integers, that sort of thing, and that's how this is built up. And we've got a lot of functions like allocate them. Are they nil? Are they a number? Are they a bool? Blah 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 blah. And these are all fine, and they're going to be used a lot in the compiler. I have some utility functions to convert them to strings because that helps with debugging. These are not actually used in the compiler at all, so they might even rot, right? They might just stop working because I've changed something and they're not tested at all. And then we've got this parser, also called a reader, that takes in a string and returns an AST. So the main function for this is this function reader read, which will take in some char star and return an AST node. And that goes through to this recursive function that does all the usual Lisp reader things. And then we've got some environment functions for binding names, such as in let, in labels, formals for code objects, and there's probably one other thing that I can't remember off the top of my head. And then finally, we get to this layer for compiling. The entry point for compiling is way at the bottom. It starts off with the compile entry. This assumes that the program you're giving it starts with the labels. This is our current restriction. So you have to say, we don't do top-level bindings in the way that you might expect in like ML or Python or C or whatever. You actually have to say, well, explicitly, these are my labels. It looks very much like a let. These are my labels with these code objects. And then the body of that is sort of the main function, if you will. And then, that calls a bunch of recursive functions for handling different types of structures, like code, like expressions, integers, characters, booleans. We'll get into more of these later. And then we've got a bunch of testing utilities, like does this compiled entry point have these byte contents? So does it contain a prologue? Does it contain the instructions we expect, et cetera, et cetera? And then finally we get to a bazillion tests. The tests are, what is this? This starts at line 1300, ends at line 2900. So, more than half of the implementation is tests, which I guess speaks to the brevity of the compiler, which is very cool, I think, even in C. And this is what we got to on my last blog post, which I published this morning. You can say, okay, here's my labels. I have a factorial function that takes in one parameter called x, and if it's less than 2, return 1. Otherwise, do the whole recursive factorial thing. And then the body of this program, which is the main function, so to speak, is this call to factorial with 5. We compile it, we make the buffer executable, and then we execute it. And then we check that the result is 120. And to take a look, what we can do is we can run okay, it's already been built. Compile it, and then the main function of this program is run the test suite, and all the tests pass, and that's really nice. Fun fact, this will not run super happily under Valgrind, and these errors are not actually programming errors. I've gone through and I've manually validated this. This is because Valgrind doesn't understand our calling convention, which is reasonable because it's kind of a weird calling convention. But I don't know, what do people want to see? I think it's just Leonard and Winona right now, my two biggest fans. let me know what you want to see of the compiler in the chat. I'm happy to go over whatever parts of it, do whatever demos, maybe even do some live development if I'm feeling brave enough. So Winona, Leonard, let me know what you want to see. If nobody answers, I'm just going to go ahead and do a walkthrough of, I don't know, compiling expressions, I guess. Maybe we'll break something and then fix it. I don't know how to intentionally break this, though. We'll see. Let's take a look at compile expr. And again, this is just an overview stream. I don't expect all of these to be sort of this unplanned and this general. I think the next stream will be me building something, me explaining how I built something. Actually, that's a good idea. I'll do that. I'll explain how procedure calls work. Leonard, no. I have integers, booleans, characters, and yeah, integers, booleans, and characters. I don't have a lot of functions on characters. Like I don't, and I should have strings at this point if I'm following along the tutorial, but I don't because I didn't want to. I wanted to go to procedure calls. But why do you ask? I can give a bit of a tour of the types that this does support via the tests. So let's see. This is parsing, blah, 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 blah. Okay. Compiling integers. Make an integer, compile it. It should move it into, this is wrong, this should say RAX. It should move it into RAX, the result register. Compiling characters, make a new character, compile it. It should move the immediate representation into RAX. So for integers, that is no, I do not do type checks. Leonard asks if I do any type checks when doing plus true 25. Let's take a look at plus. The implementation of plus is very stupid. It takes this operand 2, which it assumes is an integer, or sorry, it takes this operand 2, which, you know, if you have plus, you know, expression 1, expression 2, operand 2 is this. It'll take operand 2, compile it, and it assumes the result is going to be stored in RAX. So this is compiled, the resulting code puts the value in RAX, and then it emits an instruction to store that on the stack. So take what's in RAX and put it at some offset to the stack pointer. Then it takes, and the reason it does that, by the way, is because if you go ahead and compile operand 1, then operand 2, or the other way around, RAX will get overridden. So your result register will just get blown away by the other operand. So you have to store some temporary value. I'll get to the underscore function in a second. But you compile operand 2, you store it on the stack, you compile operand 1, storing that up, giving it temporary space on the stack, but the result is going to be in RAX. And then you add the stack location from the first, sorry, operand 2 to operand 1. And the add is just an add. It emits an add instruction. That's just no type checking, nothing. And this is because we don't have any facilities for error handling in the generated code. I think that comes after closures, after tail calls, maybe, because the Ghuloum tutorial says, okay, for error handling facilities, you could probably just do some foreign function call, like write something to standard out using the write syscall. or the C library function, and then abort. But we have nothing like that, nothing at all. No error handling. The underscore function is this fun little invention that's, the reason it exists is because I have all these calls to compile, like literally everything does a recursive call to compile. And it would be super annoying if every time I had to do if compile blah 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 is an error, return error. Like, that sucks, and it's a lot of code. So this compile macro, oh, that didn't work, says, okay, execute the expression, save the result in some result thing. If it's non-zero, that means if it's an error, return it, so propagate that back up the stack. Otherwise, just keep going. So most things don't error at all. Like, none of these things are going to have compiler errors. And things you might have compiler errors for right now are very limited. They are things like not being able to find a variable in your variable environment. Like, if you just say, like, I don't know, +1 foo, foo is not bound, doesn't know what foo is, doesn't know how to emit code for foo. So it just returns -1. There's not even a print to standard out or standard error or anything, because, I don't know, I feel like I should have better error handling facilities in the compiler, and I just never get around to doing that. Maybe that'll be another future post. So that underscore function, in short, helps with error propagation. It's sort of like a poor man's try-catch in C without the set jump long jump. Everything's a result. I don't know, what else would people like to see? I did just get label calls working, so we can talk about that. This is the thing that actually initially got me so stuck on the first version of this compiler, which was in Python, and I was working on it much earlier this year. I got so stuck on label calls and procedural calls. Oh, hey, Taylor. Welcome. Taylor has entered the chat. Wow, this is a fun mix of people. Label calls I got so stuck on several months ago that I just abandoned the compiler completely and didn't look back. And then finally I said, all right, I'm going to do this the right way. I'm going to do it in C. I'm going to just do it step by step with a bunch of tests. I had no tests the last time. And I finally got label calls working, so that's really, really nice. So label calls, for people who didn't see the last post, are sort of the C function calls. You know, you're supposed to have these first-class functions in Lisp, and these functions that can close over free variables, so you can do like let a be 1 in some lambda that takes no parameters and returns a. And why you would do that, I don't know. Maybe you just want to have this function that returns, I don't know. There's a lot of reasons you would do it. I think people do it for encapsulation, for like some fake object-oriented whatever, for, I don't know. But we don't support this right now. This is a stepping stone to get there. What we do support is procedure calls. So you say labels my procedure is some code object that takes no parameters and returns 1. And then you can call it. And that'll return 1. But it can't close over any variables or anything like that. I am working on that right now in compiling closures. So if you see this closure thing, oops. We're modifying the language so that code objects take both parameters, as they currently do, and free variables. So you say let's see, compile code. So you take this code object that looks like this, take some formals, parameters, and it takes some free vars, and then they're passed like parameters. It's pretty weird, and the reason is it's the free vars are stored in a different place. They're not stored on the stack. They're stored as an offset to the current closure. And the current closure is some, just like you have a stack pointer, RSP, you have some closure pointer for every frame, which is, we've just chosen RDI. I think that's because it's one of the registers that's callee save, so I don't know, it's just easy to reason about. And every time you have a lambda that closes over variables, you transform it into this code object that takes formals and free vars and then reads from them appropriately. So that you have to read from a different location than you would with a formal. And that looks like, for closure, this is a sort of a tagged piece of memory that just has the values one by one after another in memory. But to actually pull them off a code object, so formals are stored as negative offsets from RSP. The stack goes down. So every RSP 0 is the return address, and then from there you have RSP -8, -16, blah, blah, blah. Those are all the formals. Maybe also locals too, with let. And with the free variables, you store them as positive offsets from RDI, which stores this pointer to the closure. And then you go through and you bind them at increasing multiples of 8 from RDI. And then when you want to look up a variable in the environment, there's, they'll either be positive offsets or negative offsets, and the negative offsets are stack allocated variables, because we shouldn't be reaching sort of past our current frame. If you do RSP +8, you're reaching into your previous frame, and that's sketchy, or dynamic scope, and we're not doing that. So if you have a negative, it's an offset to RSP, it's a stack variable, and if you have a positive, it's an offset to RDI, it's a free variable, it's from the current closure. And we can see that in compile expression. Where did it go? Oh, okay, so C tags is kind of weird. That went back to compiling binary, which is an earlier stage. So let's just go to it with a bunch of, come on. Where are you? Seriously? I'm very confused. I don't know where it went. Okay, there we go. There's a couple cases. We're talking about looking up variables. As an expression, if you're a symbol, you're assumed to be a variable. So you get the current C string, which is stored in the symbol in the tree, and you look it up, and you know what register to look from, but as I said, depending on if it's positive or negative, and then you do a load. So you move into RAX some RSP minus whatever, or RDI plus whatever. That's what I'm working on with closures. Currently I don't have support for calling procedures with a current closure, but the tests for code objects seem to work. So you can say, like, I don't know. You can say, okay, I have piece of code. It takes one parameter and it takes one closure argument, one free variable. First thing it does is it looks up and then it adds them together. It looks up the second operand, so it moves first thing in the closure. RDI plus 0 is the address of the function, or sorry, the address of the function in the code. So RDI plus 8 is the first free variable in the closure, and then it moves it to some temporary stack location, and then it takes the first operand, which is a stack variable, puts it in REX, and then it adds that temporary to REX, so thereby adding the two numbers together. So we can compile these just fine, we just can't call them yet. What else do people want to look at? Is it time for bread? It's almost halfway through the stream. Are you ready to watch me completely fail with my ad hoc phone OBS nightmare setup? Let me know in the chat. Hopefully for my next stream I'll have some better equipment, like I'll break out the old camera for video. I'll have a lapel mic. It'll be nice. Maybe I'll even have a tripod. But for now we have camera hanging from the cupboard, or phone camera hanging from the cupboard. I'm gonna get ready to set up the phone camera just in case people want to do bread, so we have minimal overhead. So give me a hot sec. Alright, let's see if this worked. I'm just going to go ahead and transfer scenes to the phone, and then we'll start making bread. Once I leave the computer and the phone is filming, I have no control over the stream, and I can't even see the YouTube chat, so I don't know. I guess I'll just check in after 5 minutes or something like that. Oh, great. I should rotate the screen, huh? Or you can just deal with it being sideways. We'll see, we'll see. We had most of the ready lower but it is a little less. East, water, and the sink.
we're going to make some connections. We also have a kitchen scale, which is more precise metric with volume. So you get to use customer. Any complex will do just fine. But you have to make sure to look up our conversion online to make sure that you're not compressing the flower. It's just flower is very compressible, so you can make a snowball basically and do a number like that. We'll use stupid stuff, and we'll do that. We're going to make a basic bread to show sourdough might come in the future if this channel doesn't die. But what we do first is we're going to do and we're doing bread, actually 500 ratios from there. So use this platform. And 16% water. Depending on dough handling skills, minor middling, some to 80. We're going to start off with yeast, and because we're doing a 500 gram dough, and 1% of 500 is 5, we're going to do 5 grams of yeast. I'm watching the work worth. And we do 5 grams. Next, we're going to add some warm water. This was in the fridge, as I recommend you keep your yeast. That keeps it fresh. This is for those that don't really know what I'm doing with keeping it fresh. It's fine. We're going to add more water, and then coming back to the computer and book and hear me, see me, understand what's going on. But first, I need a vessel to hold that water. So I said we're going to do a heat test. Water, which means 400 grams water. This is from tap water in my handy dandy GitHub log. This is my place. But that's alright, that's 400 ones. Don't just much about the 1 gram of this but we're going to use it just to wake up. Get the water nice and dispersed in the butter. And I'm going to check on the chat while I do that. You don't need a bucket. This is a dough bucket. You don't need this. You need a bowl at home. Plastic bowl, whatever, glass. You need a bucket. I tell that you need the bread time. I'll be back.
Well, shit, that's unfortunate. I didn't... Okay, well, now we know for the future that I need to get some better quality headphones or something. Or, my lapel mic. I'm going to try bringing the laptop in. Why not? Why not? Let's see if that disrupts things horribly. Alright, I'm going to bring the laptop and then I'll use my mic on the laptop. Oops. Oh boy. Alright, let's bring the laptop over. How's the audio quality now? I should be back on laptop audio instead of phone audio. Okay, much better, great. Well, I'm going to do something that I don't advise, and I'm going to put my laptop on my cooking surface. Say hello to the laptop. Oh, shoot, is this still going at all? Can you see the video? Okay, it looks like the video stopped. Or do you see any motion on the... This was a bad idea. This was a bad idea. Oh no. Well, this is a nightmare. Okay. It appears as though it really didn't like that the computer moved, because I guess the internet's bad over here. Alright, maybe we'll use my laptop. Screw it. What's the worst that could happen? I'm going to add a webcam view. You'll see the extent of my kitchen. Alright, we'll see if the phone cam ever starts back up again, but for now we've got this ad hoc webcam nonsense. I'm going to put my laptop facing all of this. Okay, let me know in the chat if you can see what's going on with this new and improved video setup. I guess I'll just turn the video off my phone. Alright, I don't know. Hopefully you can see this and you're still watching. You haven't completely abandoned me. But we've got this yeast. It's sort of woken up. You can leave it for 10 to 15 minutes. I'm not that patient, so we're just going to go ahead and salt it and flour it. 2% salt in 500 grams means 10 grams of salt. So I'm just going to put... Alright, that's a little more than I expected. That's fine. I'm not that stressed about it again. I'm going to get that salt nice and dispersed. Then we want 500 grams of flour. So we're going to take this big bag and start pouring it in until we've got 500 grams. The reason I had this overhead view is because I wanted you to see what it looked like to mix this flour. Unfortunately, you will not have that privilege, but you can see what I do with my hands. To mix the flour, I normally start off with some kind of, I don't know, I give it a good shake, try and mix the water in with the flour as much as possible so that it turns into this weird slop. And this makes my life a little easier with my hands. And then I use some kind of utensil like a spatula. I don't have one of those on hand right now, so I'm going to improvise with what I see first, which is a wooden cooking chopstick. Oh dear. And then I just give it a good mix until it's... It doesn't have to be perfect, right? We're just mixing right now. We're trying to get as many of the flour bits as possible into the water, into the dough. And it's going to look gross. It's going to look like that, and that's normal. This is called being shaggy, and it'll improve with time. The goal is not to do a full kneading process either. the nice thing about this folding method that we're going to do is that you only fold it, 5 times for like 30 seconds each, and you don't have to do this 10 minutes of kneading. The kneading is sort of outdated, and takes more energy than I want to put into this. Okay, it looks, like this shaggy mess, except I don't see any obvious batches of flour. So what I'm going to do is I'm going to wet my hands. Then I'm going to fold the dough, and that means I'm going to pick it up from one side. This is really hard to demonstrate. Pull it up over the dough, put it down on the other side, rotate 90 degrees, pick it up, fold it over itself, rotate, pick it up, fold it over itself. And the first time you do this, it's not going to be, it's not going to work that well. It's going to be not very stretchy. It's going to be this sort of really loose mass, and that's fine. It'll get sort of more cohesive, more elastic, I think is the word, with time. The reason you wet your hands is so you don't end up with this. This is gross and frustrating because you have to scrape it back in. And you do that just a couple times, and then you leave the bread alone for half an hour. And then you fold like that every half hour. And you'll see after the first fold or two how different the bread will be. It will be elastic, it will be easier to fold, it will be smooth even. And then after an hour or two, it'll be nice and puffy. And it'll also have these bubbles in it, and these bubbles mean that the yeast are active, they are eating things, and that there's some fermentation going on in your dough. You want to leave it covered while it's doing that, otherwise you'll get this kind of gross, leathery, dry skin on top, and you don't want that. You want it to be damp in there. That's how you fold dough. And there's a bunch of more informative tutorials that have better AV setups on the King Arthur YouTube channel, on, San Francisco Baking Institute, that sort of thing. But I'm going to skip ahead and show you the end product, which is another loaf that I baked today. I learned this trick from cooking channels where they do some stuff live in front of you, and they're like, okay, great, we're done. Here's the thing that we did earlier with the same process. So it's not actually fully live, but it's close enough. Let me grab that loaf. This is the loaf that I baked earlier. Can you see it? It's a boule. I baked it in my cast iron Dutch oven. It's not very tall, but it does look very nice. It smells nice too. It's got a good crust. This part is hard, this part is a little softer, but it's still cooling. You want to wait, we'll get into this I guess in a future episode, but you want to wait an hour or so after baking so that the crumb can fully set on the inside and it won't be this gooey mess. I learned the hard way when I brought a loaf of bread over to Winona's house as a housewarming gift, and I was late, so I was baking it right before, and I took it out of the oven, and I got into a car, and I drove over, and then I cut into it at her house, and it was this horrible mess, and it was embarrassing to have brought over such a gross housewarming gift, but B, I also didn't know that we couldn't do that, so I thought it was undercooked, and I kept trying to bake it at her house. Anyway, Winona, I still owe you a nice loaf of bread. Let me know when you'd like to come claim it. I'm going to go back to the laptop, so I'm going to switch over video inputs to the compiler. Let me know. Oops. Let me know what y'all would like to see in the compiler before we call it an evening. I was thinking of doing an hour stream, so we've got about 10 minutes of stream left before I'm to worn out from all the nerves. So let me know. We'll take a look. Great, alright. So, in which I learned never to use Linux for live streaming. Because as soon as I plugged in my laptop to the dock, it switched over the input to the dock, which has no audio input. So I have to manually switch it back. Or I just have to write down all these tricky things that I have to remember. Anyway, what I was saying was, when I was flipping through the code, was, Leonard, you're going to be the death of me, live coding something that I've never coded before. I guess we'll learn how to compile closures. So we've got these two things. We've modified code objects so that they can read closures from the closure pointer. Now we have to modify the calls so that they can store and read from the closure pointer. And then also closure. Right now I have this implementation that doesn't do anything. It allocates and then it stores the code address, but it doesn't actually store any free bars. So this is like the dumb closure that looks like this. It's completely useless. No free bars. Let's triple check. How about now? Can you hear me now? I see the little green bars going on my mic, so I'm hopeful. So the thing to do would be to I'm reading this PDF that I can send a link to in the chat, which is what I'm doing this whole tutorial from. And I'm on section 3.9, which is on page 6. So there's this new form, fun call. Thanks, Winona, and have a nice evening. Appreciate you coming to join us. We've got this new form, fun call, that replaces label call. Fun call takes now not just a label, but some arbitrary expression that gets compiled into code. And then saves 2 spaces on the stack, return point and the closure pointer. Where does it get the closure pointer? The closure pointer probably comes, okay, that makes sense. The callable thing that you're calling will evaluate to a closure, which is the heap object. And that means that the closure pointer you take and you store on the stack right next to the return address before all the arguments. So then what? Then I guess that means we just need to get closure working. The reason I stopped working on closure with multiple, or more than 0 free bars is because there's this sort of tricky 2-step problem that we solved a little bit earlier that Leonard actually found a bug in my original implementation of cons, which is your operands could themselves allocate. So you have to make sure that you evaluate them, your operands, store them in sequential locations on the stack, and then only then do you allocate and move those stack allocated temporaries into your allocated memory. So, it's what we do here for cons, which is going to have to be very similar to what we do with closure, is compile car, put it on the stack, compile cutter, put it on the stack in a different location. So stack index minus keyword size. And then store coder. And then fetch car and store car. I think this was a, and then you go and you bump the heat pointer. And so we're going to have to do that for closure as well, except it's not bounded to 2 free bars. So I'm going to have to figure out a way to, I guess I just have to have this crappy little recursive function that allocates a bunch of stuff on the stack in sequential locations, and then I guess on the way back down from the recursion stores them in sequential locations in the what do you call it, in the closure. And then it'll return the closure and then bump the heat pointer. That's fine, I guess. So you have to make sure that if you have some function a, b, c, d, let's just do abc, that will first compile a, store a at so rsp -8, compile b, and then on the way back down, after it's done all that, it can start writing into, so it'll write function into closure, it's gonna have to write them in reverse. Write C into closure, write B into closure, write A into closure, and I guess it could build up these, just pass around some stuff from the return, so it'll just keep, it knows how many free variables it has at the end, so this is going to go into like n free vars times word size minus, current, I guess. So at the beginning, current offset will be, I guess offset's the wrong word. It's the number of layers deep in your recursion. So at the beginning, that'll be 3, and there's 3 free vars, so that'll go at 0, and then you'll go back a frame. You'll still have 3 free vars, but you'll have gone back a frame, so you're at 2, so it'll store it offset. Oh, that's backwards. No, that's, okay, I'll figure this out. But basically, build it up in the stack and then store it back into the closure. And then, only then, because there's no further allocations, you're just doing a bunch of memory writes, can you store directly into RSI, which is the heat pointer, and then bump it. Thank you, Leonard, for finding and fixing this bug in cons. It's a pain. I wonder if there's a more ergonomic way we can do this. I don't know. Anyway, that's where I'm going to call it for the stream tonight. It is 6:02 p.m., 6:03 p.m. PT. I hope this was a good BrEPL print loop, episode 0, AV nonsense. Maybe I'll have better equipment next time. Have a nice evening, morning, whatever you're having, everybody. And I will see you next time, or on Twitter, or, I don't know, wherever you normally interact with me. But thanks for being here. Have a good one.